Okay, so I'm going to topics attempted and not yet learned. It looks like about 10%, 11% of the class attempted calculating the heat of reaction from bond energies, but not successfully. So I've already set up this on my whiteboard, so I'm not going to click it, but let's pretend like I'm clicking it and come over here. The reason I did that is because I need to access a table, which I can't get from that window, so I had to get a different way. All right, so calculate the heat of reaction, delta H, for the following reaction. Methane, am I in red? Methane plus oxygen gives me carbon dioxide and water. Okay, so it's a simple combustion reaction. Now, this is the table. I had to find it. You had to get a different way. Okay, but I'll use the same one you guys are using. So methane plus oxygen. So remember now, when we're calculating the heat of reaction, this is going to be equal to the heat or the energy of the bonds made minus the heat of the energy for the bonds broken. Actually, it's the other way around. That's a bad start, isn't it? It's the other way around. Bonds broken and made, okay? I think Alex uses an E for energy, okay? Broken minus E formed, okay? Can you see bonds made and formed, same thing, okay? So this is what Alex is using. Bonds broken minus the bonds formed. That's the energies of those bonds, okay? We'll describe later on request why it goes in this form, because it's going to be negative, all right? It's going to be negative if it's exothermic, okay? And this is an exothermic reaction, so we're expecting something negative. Do you know how I know this is an exothermic reaction? Because it's combustion. This is what happens on my stove when I'm cooking macaroni and cheese, okay? I'm putting methane in there and some other gases, but it's largely methane. This is like natural gas. And we're taking oxygen out of the air, and we're making carbon dioxide and water, all right, and macaroni and cheese. All right, so what I got to do now then is make a list of all the bonds that are broken and all the bonds that are formed, okay? So first of all, the bonds that are broken in methane, I guess you have to know the Lewis structures of these, right? Bonds that are broken, you've got those, and then two O2s, right? And you've got to subtract from it carbon dioxide and water. Okay, so all I got to do is look up those numbers, make sure I'm careful with that, and I'm done. It's relatively simple if you know what these the structures of the molecules are. That's maybe the sticking point is that. Oops, uh-oh. I lost the table. Okay, stick with me for a minute. I gotta go here. Stick with me for a minute. This is gonna be a little bit cumbersome. Actually, I don't even have to do that. I can go here. I'm not even going to start this video again. I'm just going to go here, enter the student view. This is my student account. Pardon the break here. I thought I had that thing open. I did have it open, but apparently I lost it. So I'm going to come here and go to review. I'm going to click on any problem and I'm going to get the data table open, okay? So here's my data tables right here. And I'm looking for bond energies. Bam, there we are. Okay, so let's go back over here. We're looking for some carbon-hydrogen bonds first. So let's come here, and there's a carbon-hydrogen bond right there. Do you see it? 413 kilojoules per mole. So I'm going to come here. Let me do it a different color and make it easier for you to see. So it looks like it's going to be 4 to times 413, because there's 4 of them, right? 1, 2, 3, and 4. Okay, let's go back over here. Oxygen's 495 right there. So this is 2 times 495. Okay? Don't forget, if you add wrong, we're going to be in trouble. So it looks like I've got 2 carbon-oxygen double bonds. Let me come here. Where are those? There they are, 799 each. You see them? Okay, so it's 2 times 799. You see? There's one and there's the other. Okay? And then it looks like this is going to be 4 times the OH bond. And where is OH? Right here, 463 times 463. Okay? 4 times 413. Can't do that in my head. 4 times 413 is equal to 1652. 1652. 2 times 495. I can't do that one in my head. That's 990. Minus 2 times 799. I can do that one in my head. That's 1598 because it's almost 1600, right? And then 4 times 463. I can't do that. 4 times 463 is equal to 1852. Okay? All right. 1852 plus 1598 is equal to 3450. Okay? And 1652 plus 990 is equal to 2642. 2642. So minus 3450 is equal to minus 808. 808 kilojoules per mole. Okay, so we set everything up nicely, but the last thing I'm going to do is I'm just going to go through and check everything. Okay, 4 times 413, that's about 1600, sure. Yeah, that's good. 2 times 500 is about 1000. That's good. 2 times 800 is about 1600. That's good. 4 times, I don't know, 450, that would be easier, is about 1800. Yeah, that's good. Right? You see what I'm doing? I'm just saying, does this make sense? 4 times 500 will be 2000, and that's close to 2000, so those numbers make sense. Now look at this. 1600 plus 1000 is about 2600. Yeah, that makes sense, okay? 1600 plus, I don't know, 1800 is 3400. Yeah, that totally makes sense. All right, and then finally, 2600 minus 3400. Yeah. You see what I'm doing? I'm estimating. I'm just saying, does this make sense? Is it in the right ballpark? So yeah, it looks like I did all my math correctly. It's minus 808 kilojoules per mole, and I'm certain of that. So I'm going to go ahead and turn it in and get my A and move on to my next course. All right, I hope that's helpful.